Good afternoon and welcome any viewers. I'll answer any questions related to the live stream. Anything else? Maybe. Okay, what are we going to do today? Well, first thing I'm going to do is get rid of this. Let's go to the last two streams ago. Let's get rid of this. Let's get rid of that. Let's get rid of that. We're creating a game in Common Lisp and C, and we're taking our time in it with it. And there is a Lisp game jam, Autumn Lisp game jam underway. I'm not participating. I'm just getting everything ready. Last stream, I talked about smooth movement in one dimension. Well, what does that mean? Basically, it means that if you have some sort of, let's see, sprite, that it will not come to an abrupt start necessarily, or an abrupt stop. And so we have what I'm calling velocity profiles. Let's go through all of these. I call it velocity functions, velocity profiles, and so on. In our discussion below, we'll let t be the time duration until it's our sprite stops, and v sub m is the maximum sprite velocity. Other functions have other parameters, but these two parameters are common to all of them, or most of them. Certainly t is. Okay, so parabolic, you have just a simple 3-point parabola at time 0. Your velocity is 0. Halfway through, you're at maximum velocity, and at t, your duration, you're back to 0. So a smooth ramp up, smooth ramp down. Here's an example with all of our velocities are in pixels per second, and time is in seconds. So here we have 4 pixels per second and duration of 10 seconds, and we have a parabolic curve, which we fit to it. And A, B, and C, this is our function, and boundary condition, I'm not going to call them boundary conditions because that actually means something else. Just our conditions that are endpoints. Like I said before, x dot, which is our velocity, is at 0 is 0. Halfway through, it's at the maximum, and then finally at the very end, it's back to 0. And A, B, and C are easily determined. So hyperbolic velocity curve is where we start moving fast, drop off quickly, taper off slowly. And this is the function that I chose for that. So x, do I have it parameterized with t? Oh no. So yeah, it's parameterized. T is the input. Kind of goes without saying if it's time derivative. 1 over a t plus b. A and b are parameters that scale and translate hyperbola determined from the conditions we're at our maximum when we start at 0, maximum velocity, and at the very end we are at some small number. And since, yeah, some small number, very close to 0. Okay, there's the parameters right here, or schematic here. hyperbolic velocity curve with the same maximum velocity and duration, t, and with epsilon is 0.25 pixels per second. You can see what we have here. Okay, another velocity profile, which is a little bit, it was not continuous. It sort of serves the same function as parabolic, but a little bit more customizable, but not continuous. And I call it a sustained decay velocity function. And it's just 3 line segments. So we go from 0 to maximum velocity at time t0, and from time t0 to t1 we stay there, and then from t1 to the very end of our period, or not period, to the end of our duration, we ramp back down to 0. So the function is represented like this. Oh, one other one that I didn't mention was straight line. So that I didn't draw a diagram for that, but let's do that here. So it's very simple. Let's draw our velocity axis here and time axis here, and so at time 0 and let's go red here. At time 0 we start at what I'm calling V0. So we might start here, and we ramp down over the duration to V1. Ramp down or up. So if V1 is less than V0, then we might be something like this. So here's T here. Or otherwise, if we start lower and go higher, maybe like this, or we can just stay the same velocity throughout the entire duration. It can be represented with attack sustained decay. In some cases, if let's just say that attack sustained decay is more general. Okay. So to determine position, this is the the math. Determine position. We integrate from, well, let's bring up paint again. We do this from 0 to t of x dot of t. We do that. Now this t and that t are different. So maybe I should use another, you see this a lot in textbooks where this variable, one of the limits happens to just be the same as what's the variable that we're integrating with for. So let's, and it can't be to big T because big T is the very end. This is let's just do this. Let's say, so x of, let's just call it S, is this. Okay. And equals. That's the position in one dimension. And I'll explain about the reasoning for one dimension later. By default, in this framework we have, C code, by default it uses Euler integration. Which is, let's see what we have here. Integration. Euler method. Should we go to Wikipedia? You can look it up on Wikipedia. It's very, very simple. It's that, except the variables here are different. F is, in this case, it's x dot. And in our case, in the general case, it will take the current time and the current position. Now, y is our position, so in this case, it should be x. So, but we don't use that. We just it's only f of t. In our case, so let's so this in our notation is x n plus 1 equals x n plus delta t x dot of t n my delta t n t sub n. And so delta t can be any suitable small number. It's not the greatest. There's an illustration. The error can accumulate. If you what we have here are large step sizes. If you decrease the step sizes, this red curve would follow the blue curve more closely. That's the default. But you can also override it. For instance, for a straight line function, very easy to integrate. So here's your here's what the complete velocity profile looks like, and at any time tn, you just determine this area here, trapezoid. Okay. And when to stop moving? We stop moving when we get really, really close to t. When our current time instance is close to is close to the duration. Now, in C, we have implemented this in C, or I have. Oops. Do we have it here? No. Okay. I think this code in the blog, which the blog is, a link is given in the live stream description. Let's check and see if we have any viewers. I don't have any chat. I have one. Waiting? Watching? I don't know. Let me go back here. Could be me. Okay. I want to leave that on because. Okay, so there's a very crudely implemented object-oriented type of framework that I have in C. Let's start with what I call movement structure. My convention is I don't think this is duplicated here, but FN means function pointer. So we have what's really a V table right here. We have the current velocity, we have the current displacement function, so that's BT, XT, and then we have a stop test. The displacement function updates current displacement in pixels. Current time is stored in our structure. Current velocity, these two are constant. Step size, that's delta t, and the total duration. And okay, so for these really, I use unions instead of derived classes, and we'll get to that in a second. So some of these velocity functions have parameters A, B, C for parabola actually turns out to be 0. So there is no C. Straight line has parameters A and B, all determined from the initial conditions. Hyperbola has parameters A and B, and so on. We have a little type tag here, velocity type, which is one of these: random, line, parabola, hyperbola. I did not implement attack, sustain, decay in C. So for line, parabola, or hyperbola, we just have the A and B parameters in a struct. So we have a giant union. We have unions here. If we have parabola or hyperbola or random, we have maximum and minimum velocity, although this that's not quite right, because for parabola it's just maximum, the minimum would be 0. And the little notation const here means that that's just not changed for the life of whatever, for the life of any instance of this structure. And if we have a line, we have a beginning velocity, also known as T0, ending velocity, also known as T1. Okay, I'm not going to go through these initialization function prototypes, but all they do is they create instances of a movement struct based on which one of these types you want to create one for. Okay. An example implementation for random. Oh, I didn't cover random, did I? Random velocity. What is that? That is, let's get our axis here, and get our other axis here. That is a set of randomly varying instantaneous velocities which are clamped between a minimum. So here's a minimum and a maximum. Not very interesting. So it might be something like this. Let's use this. So it might be something like that, which would give you a sort of jittery movement. Start and stop. We went down. So that's what random is. So in my blog post, I describe how to implement random. Okay, so we have a default stop test that's used by random. It's just the duration minus the current time is some small number. And then random velocity, this is the current velocity function. Where are we here? Okay. So here we're initializing vtable right here, these three statements. Random velocity, all it does is it just picks a random number between min and max, which is that. Okay, so then there's a higher level function which will operate with any type of velocity profile or movement struct, and that's called update move. I'm not going to go through every line of code here. So basically it just calls a vtable function. There's a little bit extra. It calls one of these. It calls one or all. Yeah, it calls the current velocity function, which is past the entire struct, roughly equivalent to a this pointer. And then it calls displacement, which for random velocity we just use Euler displacement. Let's see where it is in the actual code. That's it right there. Okay. Okay, and how do you use this? Well, you just call the appropriate initialization function, which will fill in the fields for PMV, or your movement struct you pass in. So here's an example somewhere down here. I had this code. It looks at command line parameters. So let's just, you initialize, pass in a pointer to your movement struct. And this loop here is different than this for reasons I don't want to get into right now. You update the move, you do whatever you want with whatever you got, and then you keep going until it's time to stop. So I will make a little note here to change this code. This code here should match this code, and I'll explain why you have a do while loop instead of for loop or a while loop. Okay. Anyways, we have C code for. Do we have C code for straight line? Well, I said we do. Parabolic, hyperbolic, and random, I know I do. I'll convert this C code to object-oriented common Lisp because it's just very clunky in C. This stuff this the union and all of these structs and so forth, they really want to be derived classes, and I don't want to use C. So let's get started with that. And let's take a look at what the object-oriented Lisp code looks like. Okay, number one, I'm not putting in any package. I'm not doing any package-related things today. It's all going to live in CL user, which is the default package, and I have class definitions. So velocity profile, which is a better name than movement struct. This is base class. Contains members or slots in common Lisp lingo that are common to everything. So duration, the step size. Okay, a little bit of, for those of you who aren't familiar with common Lisp object system, if you provide a reader only, that means that you can create an instance of a class or a class, and the slot, for instance, duration second, you can initialize, but you can not change it unless you have a writer or accessor, which means reader and writer. Init arg means you must provide it, well, I'll show you in a second, but init arg means you must initialize it when you create an instance. Init form is sort of a default value that's assigned to the slot when an instance is created. Okay. And a doc string must be at the following the slots. And I believe each slot can have a doc string as well. I'm not going to do that right now. Okay, so a line profile is the simplest. So its initial argument. This should be, I would say this should be a reader, and this should also be a reader. Okay, and we call it V0, and the convention here is whenever I have something that has some sort of units, the units are a suffix on the slot name or variable or whatever. PXS means pixels per second. PX means pixels, and second obviously means second. Parameters A and B, those, so ideally they would go into a constructor, but, and I have somewhat limited knowledge of CLOS, Common Lisp Object System. Does not have the idea of a constructor that's built into the class. It's you wrap the construction in another function, the constructor. And that's what we'll do. And so parameters A and B are read only. Okay. Parabolic, we have maximum velocity. Obviously a reader, that's not going to, we don't want to change that at any time during the our movement. Let's get rid of this documentation for this slot, just so we can be consistent with everything else. And parameters A and B, read only. I provide documentation for the classes, so VT equals AX plus B. And then the conditions on following that. VT equals AX V, it should be AT t, and we go back up here, t, at squared plus bt. Hyperbolic. So now we have maximum and minimum. So max is VM. Minimum is just epsilon for hyperbolic. Both read only, and I'm going to get rid of the doc strings here for the slots. Slots are the same thing as fields and or members in C++. Okay. Random. Pretty obvious. Max and min. And then attack, sustain, decay. Let's put, do I really want to write all of this? I'm not going to put this documentation here for attack, sustain, decay. It's not really worth watching me type all of this in another form. But we have maximum. We have our attack duration. It's not duration, though. It's attack time. And it's attack, we'll just call it time. And, well, should we use duration? Sustain. This is sustain time. And the decay is, it follows from, you initialize, when you create an instance of this, you provide that, and the step size. Okay. Which maybe this should just be some small number, or maybe it should even be a a global def parameter. Okay, sustain time and decay time follows from the duration. So yeah, we don't need a decay time because that's just the duration minus the sustain time. Okay, and let's start our REPL here. I don't know how much we'll get through, but this is probably a good one to have a multi-part. Sorry, that's my respiratory problems. This is a good topic to have a multi-part. So let's just do one part today and let's implement random. So let's see if we can create how do we, let's make our constructors first. So let's ran v, or make, we'll call our constructors make, for example, make ran v. Okay, and we need to provide what? Well, let's go up here. Let's start with the basics. We need to provide a duration. Step size will just default to something. Duration. In C. and the class will be velocity profile. Duration in seconds is and while I'm at it, let's line all this up. It's just easier to read. Not I edit, I align. Bingo. Okay. Okay, and okay, make instance. So we return an instance of the class. Let's just test this out. X2, 3, XB, REPL. Should I get rid of this cat that shows up every time I start Sly? I don't know. Control C, Control K, and it doesn't like that. Style warning, min velocity PXS defined but never used. Okay. Of course, because I didn't finish typing. Okay. Okay, 3. So let's just make an instance, see what we get. We can inspect it. Unlike C, we'd have to write a whole bunch of code to print these things out. Or we could do it, I guess, in GDB, which is a pain in and of itself. So set F, I will call it VP. Let's call it V. And so duration, we'll say 10 seconds, minimum of 1.1 and a maximum of 4. Okay. What do we have here? Warning, undefined. Okay, warning condition. Well, that's just a warning. Unbound variable V. I don't want to use def parameter. I just debugger entered. Oh, okay. I did not see that on the top. Min velocity. Okay, that's quit. Okay, that's min velocity PXS. Okay, 3. All right. Min velocity PXS. Okay, and I guess we don't have a slot. For min, but we don't have a slot. Why not? Okay. Now I think we can inspect the class also. I don't know how to inspect the class. I mean, this is a meta programming system. So the class itself is data as well. It's not just something that, excuse me, is available to the compiler. Let's put this over here. But it's claiming, oh, well, clause, it's implemented as a set of macros, and the error checking leaves a lot to be desired. But in case you didn't catch that, I called the init arg. I gave the init arg the same name as max velocity, and it didn't bother to tell me that that's a problem. Okay, there it is. We can inspect it. And what is our step size? Is unbound. So, okay, we should fix that. True step size, I'll explain that in a little bit. Min and max are set. Current displacement is 0. Current time is 0. And the current velocity is 0. And this is why we have a do while loop, is because we update. Why we will have a do while loop and why we have a do while loop in C is because first we update to get the current velocity, the displacement. At the very start of everything, the current velocity should be correct. It's not 0. We'll get to that. It's just I don't want to call it an edge case, but it's just one of those. It's a fence post thing. Looks good so far, except we should set the step size. Let's go up here. No, not there. Let's go up here. Is it def var or def parameter? Let's say def parameter. How about def const? Def constant. Okay. I think the convention is to put plus signs around constant. And we'll make it, what do I do in C? Take a look at C code. Where did I set this? I set it in the calls when I create these, which maybe that's constant is whatever I set it to on the command line. Okay, 100 milliseconds, I guess, 0.1. And let's append the units. Okay. Look at that. That is, it somehow knows that I'm creating an instance. Look at if you look at the mode line here, it looks the sly or whatever when it gives me the signature. It knows that it will list all the slots that you have to provide, which is nice. You would expect in a dynamic language that wouldn't do that, but somehow it knows. So it has step size seconds. Okay, so we'll just step size in seconds plus. Let's see if it's smart enough. No. Plus. Well, it doesn't know about it because I didn't compile it. Still, oh, there it is in lowercase for whatever reason. Okay. give it another shot. Just see if it initializes everything properly. And no. Unbound, still. Okay. Okay, is this, I have it as a read-write, so I have accessor. Step size second. Okay. Maybe I should recompile. Thought I did. Okay. There we go. Okay, step size is set. Okay. Let's go back to C code. I think in this stream we'll just get random and the sort of coordination functions working. Stop around what for me will be dinner time. It's currently 5 after 4, or roughly 4 after 16:04. We'll stop. I usually eat dinner around 1800 hours. And it should start getting dark around here by then. Certainly after daylight savings time it will. Okay, so we'll go to our C code. No chat yet. Let's see how many people I'm putting to sleep here. Turn the sound down. All right, one person. That's all right. One person's okay. We get later views. Sometimes we get comments. Okay, let's go to this random. So let's are we initializing it in the same way we initialized in the C code? Okay, so we have a section here. Okay, so let's see, current displacement, those are, let's check our slots, init current displacement and init form, and we have an access, so it defaults to 0. It's nice that we can put that in the class, in the current time in the class, the slot definition. We will not, our vtable, we're going to use generic functions, which are one of the best features of Common Lisp object system. I'll explain why later. Okay, and yes, okay, so let's set the current velocity. Let's init arg. No. Current time always starts out as 0. Current velocity doesn't start out at 0. It should start out as just what we did over here. The whatever velocity we start off with. It might be the maximum, it might be 0, might be something else. In this case, it's something else. It's some random number. So let's make this an argument that we must initialize, a slot that we must initialize. We'll call it the same name as the slot. Okay. Okay, so now we need this random between. So let's let's start off by giving each these are their own sections. I think 3 for a section. I'm not going to monkey with Emacs. But we'll do this. So I have each type as each type of profile is they're all grouped together, and we'll just okay. Def on random tween. Let's see what we got here. What does it take? It takes optional arguments and it takes a random state. What does it return? Well, what is arg? Well, we're going to have to look it up. Let's bring up the hyperspec, which hyperspec is the linked common Lisp reference. Sometimes it's useful, sometimes not. Random. Limit. Okay. Is it a inclusive limit? Random limit, a positive number or positive float. Okay, so it returns a pseudo random. Oh. No. Returns a pseudo random number that is non-negative number less than the limit and of the same type as limit. Okay, let's try it out. 3, 100, 92, 44, about 0.1. Okay, so it has like some magic stuff built in, determines whether or not to use integers or positive integers or 0 or a floating point. Okay. So we'll do this random between. I'll call it, and let's copy this comment, and we'll put it in a doc string. Okay. Is that the right way to do doc strings in Common Lisp? Let's see. Learn Lisp the hard way. Okay. I just want to see an example. There we go. There's a doc string. Okay. So there's no documentation keyword like classes. I guess because, well, probably because the time they defined Common Lisp, there were already most implementations just assume that a string was the first the first piece of a def on, then that's the doc string. But what if you want to return or a constant string? I guess you'd have to do, you know, like what, right, like that, because otherwise, you know, if you wanted to return this thing as the value of ran between, right? I mean, let's try it. Let's see what happens. Maybe it's smart. Maybe it knows if that's the only thing, then it will return that string. Let's see. Yeah, that's fine. Style warnings. What do you know? It's smart. Okay. But let's write this function here. Well, let's just return low. Okay. See what it does. 3. And yeah, okay. Not bad. Okay. What did I do here? I returned low plus high minus low. Is there a random max? Well, random max is whatever high is, so it'd be high plus 1. But let's not duplicate the C code exactly. So we want we want something that's it's truly random. I want to clamp between low and high. I don't know. Let's see. Let's think for a minute. I'm not in my best form today, so if it looks like I'm struggling with something that's completely obvious, it's because I'm struggling with something that's completely obvious. So let's do this. We could say low. But then we'd be too high in some cases. There are a number of ways we can do this. Let's we don't need that, right? Maximum of low or let's go back to the definition of random. It's always something like this. Less than the limit and the same type of limit, a non-negative number. Okay, so that means sometimes it's going to return 0, in which case I'm just worried. Here's what I'm worried about. Here's what I'm worried about. I'm open to suggestions in the comments. Why I'm struggling with this, I don't know. Here's our max. Well, let's do this. Here's our max. Here's our min. Right, and so the numbers we get, it look like, oops, let's go back here. I don't know why I changed that line to whatever. The numbers we're going to get from rand are going to look like that. something like that. Okay, and I'm wondering if we're going to bottom out here far too much because it goes to 0. The random function goes to 0, but we don't want anything less than that. And we have the opposite problem if we just you know, added if we added the minimum to the random, then we would get something like that, and we would top off here far too much. Okay. So what we want is, now it's obvious, what we want is, we want something in this range. So this is, I don't know, D. And we want random plus 1. D plus 1, and then we just add the minimum to that. That, I think, would keep us in that range. That's what we want, I think. Again, open to suggestions for my one viewer, from my one viewer. Okay, XB, smooth, so random between, we'll get rid of all this crap, and we'll say return plus low now we do random minus high low. Do we add 1? I believe that would be it. I don't know, let's try it. Not that a few tests is going, we could put it in a loop. Let's do that. Do K0, 1 plus K. We'll do it 50 times. And we'll do a round between, I don't know, 10 and 20. So, okay, what do we have here? Do we have any 20s? Yes. Do we have any 10s? Yes. Okay, that's what I want, because the doc string says inclusive. Inclusive limits. Okay, so it looks like it's right. Do we have anything larger than 20? I don't see anything. Okay, so now that we've struggled with a completely trivial function, let's move this down here. The class should be the first thing in this section, and then all the functions, generic functions, and so forth. Let's get rid of that. Let's put our oops. Let's just do this. We'll copy it. Okay, line velocity. Okay, so now we'll go back to work. Make random is we need to looks like it compiled. Is there a balance windows? There. There we go. Good, my section showed up. Okay. Make instance, let's see if it's smart enough to min velocity, max velocity, current velocity. There we go. Let's do this. And pixels per second is rand between. You kidding me? Yeah, there. Random between min and see if everything initialized. What do we do? We low and high. What did I say? Max and min. Oh, well, maybe I should do min and max. How's that? Okay. Now it's okay. Q. Let's do it again. What's the problem? Argument to random is not low and high. And let's because. Okay. There. Current velocity is 1. Okay. Let's see if we get a different one. The next try. Current velocity is 3 pixels per second. Okay. All right. So we got that set up. Wait, did I quit out of this? Q. Let's do it one more time just to check. No, I'm not going to search backwards. Okay, let's check this. Yes, it's fine. Q. Okay. I think you could say inspect. What is it? Like star? I can't remember. There's, yeah, okay. Well, you can, yeah, that's a way you can, okay. It's kind of more convenient. Maybe that was, that doesn't, Q, oh, I'm still in the inspector. Inspect, Q, okay. Let's go back to our C code. so we've basically done this, init random. Now we need a velocity function. And this, so what we did in C was, let's get rid of some stuff here. What we did in C, let's go here, was the velocity, we just set an entry in our V table. For those of you who don't know what a V table is, it's just an array of function pointers in C++ that's hidden behind the scenes, managed for you by C++. And here we're just doing all this ourselves. And I didn't want to use C++. We don't have that in common Lisp. We have what are known as generic functions. It's a very strange and magnificent idea. I say it's strange because in C++, you dispatch when you say something like this in C++. I'll just write it over here. Maybe I should say highlight line mode. Okay, so there's my current line. When you say something like PMV, current velocity. Okay, which, yeah, whatever you pass to it. Okay, the only parameter that you're dispatching on is the implicit this parameter. In common Lisp object system, you can dispatch on any number of parameters. Specialize. We're only dispatching on the first, again, because we wrote this in, well, because we don't need to do anything other than that. But in common Lisp object system, first thing you do is to have virtual functions, is you declare def generic. So we'll define our generics here. They're called generic functions. Def generic. And the name is going to be and then you list the general form. And so the generic function is going to take a velocity profile, and that's really for the compiler. Then it's also for you. Oops, no, control this. Then you specialize that like so. So you say def method current velocity, and then you list the argument, so VP, and then you say but this function only applies, this method only applies to a random velocity profile. Okay, and we're just going to copy the code, which is dead simple. It's this. presto. Okay, so this should be the code for random velocity profile, which in my opinion is simpler than the C code. So, and our compilation failed. Why? Let's just take me to the offending line of code. Because I didn't write this correctly. Warning, undefined variable max velocity pxs. Oh yeah. Okay, a little bit clunky. Yeah, of course. Okay, so all we're doing is we're just accessing those slots of VP, stand for velocity profile, and the setF here will set current velocity PXS, the slot in VP. Undefined function, min velocity PXS. Really? Okay. Because honestly, I think that, you know, the implementation of clause should be much better. It should tell me that I defined this reader twice, but it doesn't. And looks like, yeah, okay. So let's do this, and so now we can say current velocity, and we'll just pass some random thing, nil, and it's going to complain there's no applicable method for that, which is what we want. But if we pass in v, which is a random velocity, everything should be cool.